you could theoretically miss something. Let me give a very simple example of how this works. Let's assume that we're trying to find parameters that maximize the likelihood of this dotted vertical line here at 55. And I've got three possibilities. I've got my red distribution, which is off to the left, the blue, which is a little more center, and the green, which is far to the right. And these are all identical, except they have different means. And by changing the means, you see that the one that is highest where the dotted line is the blue one. And so if only thing we're doing is changing the mean and we're looking at these three distributions, then the blue one is the one that has the maximum likelihood for this particular parameter. On the other hand, we could give them all the same mean right around 50 and vary their standard deviations instead. And so they spread out different amounts. In this case, the red distribution is highest at the dotted vertical line, and so it has the maximum value. Or if you want to, you can vary both the mean and the standard deviation simultaneously. And here the green gets a slight advantage. Now, this is really a caricature of the process because obviously you would just want to center it right there on the 55 and be done with it. The question is when you have many variables in your data set, then it's a very complex process of choosing values that can maximize the association between all of them. But you get a feel for how it works with this. The third approach that's pretty common is something called MAP for maximum a posteriori. This is a Bayesian approach to parameter estimation. And what it does is it adds the prior distribution and then it goes through sort of an anchoring and adjusting process. What happens, by the way, is that stronger prior estimates exert more influence on the estimate. And that might mean, for instance, a larger sample or more extreme values. And those have a greater influence on the posterior estimate of the parameters. Now, what's interesting is that these three methods all connect with each other. Let me show you exactly how they connect. The ordinary least squares, OLS, this is equivalent to maximum likelihood when it has normally distributed error terms. And maximum likelihood, ML, is equivalent to maximum a posteriori, or MAP, with a uniform prior distribution. You want to put it another way, ordinary least squares, or OLS, is a special case of maximum likelihood. And then maximum likelihood, or ML, is a special case of maximum a posteriori. And just in case you like it, we can put it in set notation. OLS is a subset of ML, is a subset of MAP. And so there are connections between these three methods of estimating population parameters. Let me just sum it up briefly this way. The standards that you use, OLS, ML, MAP, they affect your choices and the ways that you determine what parameters best estimate what's happening in your data. Several methods exist, and there's obviously more than what I showed you right here, but many are closely related, and under certain circumstances, they're all identical. And so it comes down to exactly what are your purposes and what do you think is going to best work with the data that you have to give you the insight that you need in your own project. The next step we want to consider in our statistics and data science and the choices that we have to make has to do with measures of fit, or the correspondence between the data that you have and the model that you create. Now, it turns out there's a lot of different ways to measure this, and one big question is how close is close enough? Or how can you see the difference between the model and reality? Well, there's a few really common approaches to this. The first one is what's called R-squared. It's got a longer name. That's the coefficient of determination. There's a variation, adjusted R-squared, which takes into consideration the number of variables. Then there's minus 2LL, which is based on the likelihood ratio, and a couple of variations, the Akaike Information Criterion, or AIC, and the Bayesian Information Criterion, or BIC. And then there's also chi-squared. Now that's actually a Greek C there. It looks like an X, but it's a C, and that's chi-squared. And so let's talk about each of these in turn. First off is R-squared. This is the squared multiple correlation, or the coefficient of determination. And what it does is it compares the variance of Y. So if you have an outcome variable, it looks at the total variance of that and compares it to the residuals on Y after you've made your prediction. The scores on R-squared range from 0 to 1, and higher is better. The next is -2 log likelihood. That's the likelihood ratio, or as I just said it, the -2 log likelihood. And what this does is it compares the fit of nested models. We have a subset, then a larger set, then a larger set overall. This approach is used a lot in logistic regression when you have a binary outcome. And in general, smaller values are considered better fit. Now, as I mentioned, there are some variations of this. I like to think of variations of chocolate. The -2 log likelihood, there's the Akaike information criterion, the AIC, and the Bayesian information criterion, BIC. And what both of these do is they adjust for the number of predictors. Because obviously, if you have a huge number of predictors, you're going to get a really good fit, but you're probably going to have what's called overfitting, where your model is tailored too specifically to the data you currently have and doesn't generalize well. These both attempt to reduce the effect of overfitting. And then there's chi-squared again. It's actually a lowercase Greek c, looks like an x. And chi-square is used for examining the deviations between two data sets, specifically between the observed data set and the expected values, or a model you create of, we expect this many frequencies in each category. Now, I'll just mention, like going to the store, there's a lot of other choices, but these are some of the most common standards, particularly the R-squared. And I just want to say, in sum, there are many different ways to assess the fit, the correspondence between a model and your data. And the choices affect the model, especially, are you going to penalize for throwing in too many variables relative to your number of cases? Are you dealing with a quantitative or a binary outcome? Those things all matter. And so the most important thing, as always, my standing advice is keep your goals in mind and choose a method that seems to fit best with your analytical strategy and the insight you're trying to get from your data. The statistics and data science offers a lot of different choices. One of the most important is going to be feature selection, or the choice of variables to include in your model. It's sort of like confronting this enormous range of information and trying to choose what matters most, trying to get the needle out of the haystack. The goal of feature selection is to select the best features or variables and get rid of uninformative and noisy variables and simplify the statistical model that you're creating, because that helps avoid overfitting or getting a model that works too well with the current data and works less well with other data. The major problem here is multicollinearity, a very long word that has to do with the relationship between the predictors and the model. I can show it to you graphically here. Imagine, for instance, we've got a big circle here to represent the variability in our outcome variable. We're trying to predict it. And we've got a few predictors. So we've got predictor number 1 over here, and you see it's got a lot of overlap. That's nice. Then we've got predictor number 2 here. It also has some overlap with the outcome, but it also overlaps with predictor 1. And then finally down here, we got predictor 3, which overlaps with both of them. And the problem arises the overlap between the predictors and the outcome variable. Now, there's a few ways of dealing with this. Some of these are pretty common. So for instance, there's the practice of looking at probability values in regression equations. There are standardized coefficients, and there's variations on sequential regression. There are also newer procedures for dealing with the disentanglement of the association between the predictors. There's something called commonality analysis. There's dominance analysis, and there are relative importance weights. Of course, there are many other choices in both the common and the newer, but these are a few that are worth taking a special look at. First is p-values, or probability values. This is the simplest method because most statistical packages will calculate probability values for each predictor, and they'll put little asterisks next to it. And so what you're doing is you're looking at the p-values, the probabilities for each predictor, or more often the asterisks next to it, which sometimes give it the name of star search. You're just kind of cruising through a large output of data and just looking for the stars or asterisks. This is fundamentally a problematic approach for a lot of reasons. The problem here is you're looking individually and it inflates false positives. Say you have 20 variables, each is entered and tested with an alpha or false positive of 5%. You end up with nearly a 65% chance of at least one false positive in there. It's distorted by sample size because with a large enough sample, anything becomes statistically significant. And so relying on p-values can be a seriously problematic approach. Slightly better approach is to use betas, or standardized regression coefficients. And this is where you put all the variables on the same scale. So usually standardized from 0 and then to either -1, +1, or with a standard deviation of 1. The trick is, though, they're still in the same context of each other, and you can't really separate them because those coefficients are only valid when you take that group of predictors as a whole. So one way to try to get around that is to do what they call stepwise procedures, where you look at the variables in sequence. There are several versions of sequential regression that allow you to do that. You can put the variables into groups or blocks and enter them in blocks and look at how the equation changes overall. You can examine the change in fit at each step. The problem with a stepwise procedure like this is it dramatically increases the risk of overfitting, which again is a bad thing if you want to generalize your data. And so to deal with this, there's a whole collection of newer methods. A few of them include commonality analysis, which provides separate estimates for the unique and shared contributions of each variable. Well, that's a neat statistical trick, but the problem is it just moves the problem of disentanglement to the analyst, so you're really not better off than you were as far as I can tell. There's dominance analysis, which compares every possible subset of predictors. Again, sounds really good, but you have the problem known as the combinatorial explosion. If you have 50 variables that you could use, and there are some that have millions of variables, with 50 variables, you have over 1 quadrillion possible combinations. You're not going to finish that in your lifetime. And it's also really hard to get things like standard errors and perform inferential statistics with this kind of model. And then there's also something that's even more recent than these others called relative importance weights. And what this does is it creates a set of predictors that are orthogonal or uncorrelated with each other, basing them off of the originals. And then it predicts the scores, and then it can predict the outcome without the multicollinear because these new predictors are uncorrelated. It then rescales the coefficients back to the original variables. That's the back transform. And then from that, it assigns relative importance or a percentage of explanatory power to each predictor variable. Now, despite this very different approach, it tends to have results that resemble dominance analysis. It's actually really easy to do. Their website, you just plug in your information and it does it for you. And so that's yet another way of dealing with the problem of multicollinearity and trying to disentangle the contribution of different variables. In sum, let's say this. What you're trying to do here is choose the most useful variables to include into your model. Make it simpler, be parsimonious. Also, reduce the noise and distractions in your data. And in doing so, you're going to always have to confront the ever-present problem of multicollinearity or the association between the predictors in your model with several different ways of dealing with that. As we continue our discussion of statistics and the choices that are made, one important consideration is model validation. And the idea here is as you're doing your analysis, are you on target? More specifically, your model that you create through regression or whatever you do, your model fits the sample data beautifully, you've optimized it there, but will it work well with other data? Fundamentally, this is the question of generalizability, also sometimes called scalability, because you're trying to apply it in other situations. And you don't want to get too specific or it won't work in other situations. Now, there are a few general ways of dealing with this and trying to get some sort of generalizability. Number one is Bayes, a Bayesian approach. Then there's replication. Then there's something called holdout validation, and then there's cross-validation. I'll discuss each of these very briefly in conceptual terms. The first one is Bayes, and the idea here is you want to get what are called posterior probabilities. Most analyses give you a probability value for the data given the hypothesis, so you have to start with an assumption about the hypothesis. But instead, it's possible to flip that around by combining it with special kinds of data to get the probability of the hypothesis given the data. And that is the purpose of Bayes' theorem, which I've talked about elsewhere. Another way of finding out how well things are going to work is through replication. That is, do the study again. It's considered the gold standard in many different fields. The question is whether you need an exact replication or a conceptual one that is similar in certain respects. You can argue for both ways, but one thing you want to do is when you do a replication, then you actually want to combine the results. And what's interesting is the first study can serve as the Bayesian prior probability for the second study. So you can actually use meta-analysis or Bayesian methods for combining the data from the two of them. Then there's holdout validation. This is where you build your statistical model on one part of the data and you test it on another. I like to think of it as the eggs in separate baskets. The trick is that you need a large sample in order to have enough to do these two steps separately. On the other hand, it's also used very often in data science competitions as a way of having a sort of gold standard for assessing the validity of a model. Finally, I'll just mention one more, and that's cross-validation. This is when you use the same data for both training and for testing or validating. There are several different versions of it, and the idea is you're not using all the data at once, but you're kind of cycling through and weaving the results together. There's leave one out, where you leave out one case at a time, also called LOO, L-O-O. There's leave P out, where you leave out a certain number at each point. There's K-fold, where you split the data into, say, for instance, 10 groups, and you leave out one and you develop it on the other 9, and then you cycle through. And there's repeated random subsampling, where you use a random process at each point. Any of those can be used to develop the model on one part of the data and test it on another, and then cycle through to see how well it holds up under different circumstances. And so, in sum, I can say this about validation. You want to make your analysis count by testing how well your model holds up from the data you developed it on to other situations, because that's really what you're trying to accomplish. This allows you to check the validity of your analysis and your reasoning, and it allows you to build confidence in the utility of your results. To finish up our discussion of statistics and data science and the choices that are involved, I want to mention something that really isn't a choice, but more an attitude. It's DIY for do it yourself. The idea here is, really, you just need to get started. Remember, data is democratic. It's there for everyone. Everybody has data. Everybody works with data, either explicitly or implicitly. So data is democratic. So is data science. And really my overall message is you can do it. A lot of people think you have to be at this totally cutting edge virtual reality sort of thing. And it's true. There's a lot of active development going on in data science. There's always new stuff. The trick, however, is the software that you can use to implement those things often lags. It'll show up first in programs like R and Python, but as far as it showing up in a point-and-click program, that could be years. What's funny, though, is often these cutting-edge developments don't really make much of a difference in the results of the interpretation. They may in certain edge cases, but usually not a huge difference. And so I'm just going to say, analysts beware. You don't necessarily have to do it. It's pretty easy to do them wrong. And so you don't have to wait for the cutting edge. Now, that being said, I do want you to pay attention to what you're doing. A couple of things I've said repeatedly is know your goal. Why are you doing this study? Why are you analyzing the data? What are you hoping to get out of it? Try to match your methods to your goal. Be goal directed. Focus on the usability. Will you get something out of this that people can actually do something with? And then, as I've mentioned several times with the Bayesian thing, don't get confused with probabilities. Remember that priors and posteriors are different things, just so you can interpret things accurately. Now, I want to mention something that's really important to me personally, and that is beware the trolls. You will encounter critics, people who are very vocal and who can be harsh and grumpy and really just intimidating. And they can really make you feel like you shouldn't do stuff because you're going to do it wrong. But the important thing to remember is the critics can be wrong. Yes, you'll make mistakes. Everybody does. I can't tell you how many times I have to write my code more than once to get it to do what I want it to do. But in analysis, nothing is completely wasted if you pay close attention. I've mentioned this before. Everything signifies, or in other words, everything has meaning. The trick is that the meaning might not be what you expected it to be. So you're going to have to listen carefully. And I just want to reemphasize, all data has value, so make sure you're listening carefully. In sum, let's say this: no analysis is perfect. The real question is not, is your analysis perfect, but can you add value? And I'm sure that you can. And fundamentally, data is democratic. So I'm going to finish with one more picture here. And that is, just jump right in and get started. You'll be glad you did. To wrap up our course, Statistics and Data Science, I want to give you a short conclusion and some next steps. Mostly, I want to take a little piece of advice I learned from a professional saxophonist, Kirk Whalum. And he says, there's always something to work on. There's always something you can do to try things differently, to get better. It works when practicing music. It also works when you're dealing with data. Now, there are additional courses here at datalab.cc that you might want to look at. There are conceptual courses, additional high-level overviews on things like machine learning, data visualization, and other topics. And I encourage you to take a look at those as well to round out your general understanding of the field. There are also, however, many practical courses. These are hands-on tutorials on the statistical procedures I've covered, and you learn how to do them in R and Python and SPSS and other programs. But whatever you're doing, keep this other little piece of advice from writers in mind, and that is, write what you know. And I'm going to say it this way: explore and analyze and delve into what you know. Remember, when we talked about data science and the Venn diagram, we've talked about the coding and the stats, but don't forget this part here on the bottom. Domain expertise is just as important to good data science as the ability to work with computer coding and the ability to work with the numbers and quantitative skills. But all through it, remember this: you don't have to know everything. Your work doesn't have to be perfect. The most important thing is just get started. You'll be glad you did. Thanks for joining me, and good luck.